In this module, we will explore the properties and behavior of vapor in equilibrium with a condensed phase, such as a liquid or solid. I will highlight the key differences in thermodynamic properties between gases and condensed phases and examine how temperature and external pressure influence vapor pressure and the stability of condensed phases. We start by discussing the distinction between vapor and gas. These terms are often used interchangeably in everyday language. However, they have precise and distinct meanings in thermodynamics. A gas is the most stable phase of a substance at a specified temperature and external pressure. It exists independently, remains stable in the gas phase under these conditions, and is not transforming into a liquid or solid. On the other hand, vapor refers to a gaseous phase of a substance that is not the most stable under the given conditions. A vapor exists in equilibrium with its liquid or solid phase, and its existence depends on the presence of these other condensed phases. The partial pressure of a vapor Pi is in most cases less than the total pressure of the gas mixture P tot, which in turn must match the total external pressure Px. The vapor phase is in dynamic equilibrium with the condensed phase. Molecules of the substance in question continuously transition between the gaseous and condensed phases. This equilibrium determines the vapor pressure of the condensed phase. The vapor pressure of a condensed phase is defined as the pressure exerted by the vapor when it is in equilibrium with its liquid or solid phase at a specific temperature. The type of dependence of the chemical potential on the amount of substance greatly differs between condensed phases, such as solids and liquids, and gases. For chemically pure condensed phases, the chemical potential is largely unaffected by the amount of substance present. This means that whether we have a small or large quantity of a solid or liquid, its chemical potential remains constant under the same external conditions. However, for a gas, the chemical potential does depend on the amount of substance through its dependence on the partial pressure. When the amount of gas decreases, resulting in a lower partial pressure, its chemical potential also decreases. This relationship is described by the following equation, highlighting the logarithmic dependence of the chemical potential of the gas on its partial pressure. Furthermore, in a phase diagram, the meaning of the term pressure is different depending on whether we are looking at a condensed phase or a gas phase. For a condensed phase, it refers to the total external pressure which influences the stability and behavior of the phase. For the gas state of the substance, however, we are looking at the partial pressure of the gas, as this determines its chemical potential. Importantly, the presence of other gases within the same gas phase does not impact the state of any individual gas. The chemical potential of each gas is solely determined by its own partial pressure. Here, I repeat the equation expressing the chemical potential of a vapor as a function of its standard chemical potential and partial pressure. This equation shows that a decrease in the partial pressure of a gas results in a decrease in its chemical potential. However, this equation also indicates that due to the logarithmic dependence on partial pressure, the chemical potential of a gas has no theoretical lower limit. Mathematically, as the partial pressure approaches zero while still remaining positive, the chemical potential approaches negative infinity. In thermodynamic terms, this implies that for any desired value of the chemical potential, no matter how negative, there exists a corresponding partial pressure that satisfies this relationship, even if that pressure is extremely low. Therefore, the chemical potential of a gas can be arbitrarily low. Thermodynamic equilibrium between a stable condensed phase and its vapor means that the chemical potentials of both phases are equal. For a given temperature and external pressure, the chemical potential of a condensed phase is fixed. By contrast, the chemical potential of a gas can decrease to arbitrarily low values. This property of gases is crucial for understanding how equilibrium can exist between a condensed phase and its vapor. Since the vapor's chemical potential can adjust to match that of the condensed phase, this indicates that an equilibrium between the vapor and condensed phase can always be established. This implies that theoretically there is always a certain amount of vapor present in equilibrium with any condensed phase, even if its quantity is minuscule. Finally, note that when we refer to vapor pressure in the context of thermodynamic equilibrium, we are specifically describing what is known as saturated vapor pressure. The concept introduced on the previous slide can be illustrated by this diagram, representing temperature dependence of the phase stability and phase transitions for a pure substance in its standard state. In the standard state, the partial pressure of the gas equals the standard value of 1 bar. If the temperature is sufficiently high, the gas in the standard state has a lower chemical potential than the liquid in its standard state. Therefore, the liquid state is not stable at these temperatures and completely transforms into gas. As we defined earlier, the gas is the only stable phase of the substance under these conditions. The temperature at which the standard chemical potentials of the liquid and gaseous phases are equal, meaning the curves of the chemical potentials for the two phases intersect, is the standard boiling point as defined previously. When the temperature is below the standard boiling point, the liquid phase in the standard state has a lower chemical potential than the gas in the standard state. This creates a thermodynamic driving force for the substance in the gas phase to transition or condense into the liquid state. As the gas condenses, the amount of gas and its partial pressure in the system decreases. As a result, the chemical potential of the gas also decreases until it becomes equal to the chemical potential of the liquid phase. The chemical potential of the gas is still described by the general equation introduced before. Here we equate the standard chemical potential of the liquid phase to the current chemical potential of the vapor. P VAP represents the pressure of the vapor in equilibrium with the liquid phase under these conditions. If the temperature changes, the vapor pressure adjusts so that its current chemical potential remains equal to the standard chemical potential of the liquid phase. When the temperature increases, the difference between the standard chemical potentials of the gaseous and liquid phases decreases, which requires a higher vapor pressure to maintain equilibrium. When the temperature decreases, the situation is opposite. The coexistence curve and the vapor pressure curve, though conceptually distinct, are represented by the same set of data and the same curve shown in the phase diagram. The coexistence curve represents the conditions, namely temperature and pressure, where a condensed phase, solid or liquid, is in equilibrium with its gas phase. Meanwhile, the vapor pressure curve specifically displays the equilibrium vapor pressure of the condensed phase at the given temperature, meaning the saturation vapor pressure. They effectively describe the same temperature-pressure relationship, and both are represented by the same curve on the phase diagram. We can demonstrate the equivalence of these two data sets with the following experiment. Let us consider a pure liquid substance at a certain temperature below its standard boiling point, in equilibrium with its gas phase, where it is the only substance present. On a PT phase diagram, this situation is represented by the liquid-gas coexistence curve. The pressure of the substance in the gas phase corresponds to a point on this curve at the specific temperature. Now we add an inert gas to the gas phase. The total pressure of the gas phase increases, but this does not affect the equilibrium between the liquid and, as we should now call it, its vapor. If we add enough inert gas to bring the total pressure to the standard pressure of 1 bar, the liquid is considered to be in its standard state. Throughout this process, the chemical potential of the liquid remains virtually unchanged, as the pressure increase of less than 1 bar is insufficient to significantly impact it. Similarly, the chemical potential and pressure of the vapor remain constant, as they are unaffected by the presence of the inert gas. Therefore, we have obtained, on one hand, the partial pressure of the substance in equilibrium with its liquid state in the standard state, as shown by the vapor pressure curve. On the other hand, this value of pressure is identical to that given by the coexistence curve between the pure liquid and the pure gas of this substance. Now, let's explore how the stability of a condensed phase, whether solid or liquid, depends on the relationship between its vapor pressure and the external pressure. A condensed phase remains stable as long as its vapor pressure is less than or equal to that of the external pressure. In this situation, molecules escape from the condensed phase into the gas phase as vapor. This vapor continues to accumulate above the condensed phase, but as the number of vapor molecules increases, some begin to return to the condensed phase. Eventually, an equilibrium is established when the rate of molecules leaving the condensed phase equals the rate of molecules returning to it. At this point, the vapor has reached a stable value known as the saturated vapor pressure. This represents the maximum vapor pressure achievable at a given temperature without causing the condensed phase to fully transform into gas. When the vapor pressure of a condensed phase exceeds the external pressure, thermodynamic equilibrium cannot be reached under constant external pressure conditions. In this scenario, the system is unable to reach the saturated vapor pressure and thus establish a balance between molecules leaving the condensed phase and molecules returning to it. The condensed phase continuously releases more molecules into the gas phase than the number of molecules coming back. To establish the equilibrium, the vapor pressure would need to be able to stabilize at a level equal to the external pressure. However, as the vapor pressure remains higher than the external pressure, the system must either expand to accommodate the evaporating molecules or, in practical terms, the vapor must be removed to maintain the constant pressure conditions. In both cases, a persistent driving force pushes the substance from the condensed phase into the gas phase, and the condensed phase ultimately transforms completely into the gas phase. Now, let's see how we can thermodynamically interpret the evaporation or sublimation of a condensed phase upon an isothermal decrease of external pressure. We begin with the initial state 1, where the external pressure is greater than the saturated vapor pressure. A condensed phase, either liquid or solid, is in a stable equilibrium with its vapor. This stability is reflected by the chemical potential of the vapor being equal to that of the condensed phase. In the state 2, we decrease the external pressure to a value which is still greater than the saturated vapor pressure. The phase vapor equilibrium remains unaffected, with the vapor pressure staying the same, and the chemical potentials of both phases remain unchanged. Continuing to reduce the external pressure, we reach the state 3, where the external pressure equals the vapor pressure. The condensed phase is still stable and the system is in equilibrium. However, now the vapor can be the only substance present in the gas phase. If we further decrease the external pressure so that it becomes lower than the saturated vapor pressure, the situation changes drastically. In this state 4, the actual vapor pressure is below its saturated vapor pressure, causing the chemical potential of the vapor to drop below that of the condensed phase. This difference in chemical potential introduces a thermodynamic force driving the phase change. The condensed phase becomes thermodynamically unstable and will spontaneously begin to transform into the vapor phase. The chemical potential of the condensed phase remains unaffected by its partial evaporation or sublimation, and so the driving force. The system can reach a new equilibrium only once the condensed phase has fully converted into the gas phase. Let's now explore what happens to the stability of a condensed phase when we gradually increase the temperature while keeping the external pressure constant. We start with the same initial state 1 as in the previous slide. At this point, the vapor pressure is below the external pressure, and the condensed phase is in equilibrium with its vapor, with their chemical potentials equal. As we increase the temperature, the chemical potential of the condensed phase begins to decrease. For the vapor phase, the chemical potential also decreases, but it does so more sharply because the vapor, as a gas, has higher entropy compared to the condensed phase. Despite this difference, the system remains in equilibrium as long as the vapor pressure rises sufficiently with temperature to maintain the equilibrium between the phases. Continuing to raise the temperature brings us to state 2, where the vapor pressure equals the external pressure. This specific temperature is known as the boiling point at the given external pressure. If the temperature increases beyond this point, with the external pressure remaining constant, the condensed phase becomes unstable. In this new state 3, the sharper decrease in the vapor's chemical potential can no longer be compensated by an increase in its pressure. As a result, the chemical potential of the vapor drops below that of the condensed phase. Similar to the situation described in the previous slide, this difference creates a persistent thermodynamic force driving the complete evaporation or sublimation of the condensed phase. How does the vapor pressure of a condensed phase change when an external pressure is applied to it at constant temperature? Increasing the external pressure raises the chemical potential of the condensed phase. The infinitesimal change in the chemical potential of the condensed phase due to an increase in external pressure is given by the equation d mu of the condensed phase is equal to Vm of the condensed phase times infinitesimal increment in external pressure dpx. We assume the molar volume of the condensed phase to be constant. Since the condensed phase and the vapor remain in equilibrium, The change in the chemical potential of the vapor must be equal to the change in the chemical potential of the condensed phase. This change in the vapor's chemical potential can also be expressed as RT times dP vap divided by P vap. In the next step, we integrate the leftmost and the rightmost terms of this equation from the initial to the final values of the external pressure. Both integrations are straightforward and lead to the following equation. RT times the natural logarithm of the ratio of Pvap to Pvap asterisk is equal to the molar volume of the condensed phase times Px minus Px asterisk. Here, Pvap asterisk represents the initial vapor pressure at the initial external pressure Px asterisk, and Pvap is the adjusted vapor pressure under the new external pressure Px. And this equation shows how the vapor pressure depends on the external pressure exerted on the condensed phase. Pvap is equal to Pvap asterisk times the exponent of the molar volume of the condensed phase divided by RT times Px minus Px asterisk. Namely, it tells us that the vapor pressure increases when a higher external pressure is exerted on the condensed phase. The result presented in the previous slide reveals an interesting aspect of equilibrium behavior that seems to contradict the straightforward predictions of Le Chatelier's principle. Le Chatelier's principle suggests that a system at equilibrium will adjust to counteract any imposed change. According to this principle, increasing the external pressure on a system in equilibrium would seem to imply that the system should react by reducing the amount of vapor. However, the considered system doesn't decrease the amount of vapor to resist the increase in external pressure. Instead, it responds by raising the equilibrium vapor pressure, as we have previously demonstrated. This example serves as a reminder to exercise caution when applying simple rules like Le Chatelier's principle to real systems, as their responses can be driven by a complex interplay of multiple factors.